this two-part video we're going to be taking a detailed look at the steam turbine powered propellant pumps used in the world's first ballistic missile, the turbo pump of the infamous V2 rocket. The turbo pump was one of the most critically demanding developments in the evolution of the A4, later known as the V2 missile. In fact, someone once said, with only a little exaggeration, that a liquid-fueled rocket engine was a turbo pump with just a few other bits and pieces bolted on. The turbo pump is seen here extracted from the plumber's nightmare of pipes and valves, but we're going to confine it still further as we won't be discussing the liquid oxygen valve and LOX distributor, so let's remove those items. And we won't be saying much about the tanking connections, so let's remove the metal bellows at the propellant intake flanges as well. That leaves us with the turbine-powered pumps, plural. It certainly is one big singular lump, but in fact it's two separate pumps powered by the same central steam turbine. But first, let's get an overview of the components of the turbo pump system.
Okay, let's quickly take it to bits before we actually put it back together again. What I want to show you here is the fundamental components of the turbo pump. What we're looking at here is the turbine, the steam turbine system. All I probably want you to pick up from this is that the turbine rotor in the center there, very easily visible. The green part here is actually the rotor. I've got you another little cardboard cutout so that you can see that in a bit more detail, but the turbine rotor actually sits inside that case just there, and we can see at the tip here the rim of the turbine rotor has two sets of steam buckets, a little one and a big one. We'll look into all of that a little bit more later, so put your notebooks away for now. We're going to look at this in a bit more detail in just a moment. Let's just put the steam manifold on there, so the steam comes in from the 360 degree manifold on the left and is passed by pipes into an inner steam manifold that distributes the steam onto the nozzles. We can actually see one of the steam nozzles just here passing into this row of steam buckets. Over here on the right, onto that weighting shaft, heavily splined to receive it, will fit the fuel pump. This is a centrifugal style pump. We can see the impeller here in blue. Other little details to pick up here is the shaping of the volute case that is transferring the fuel that is coming in at the top here, passing into the eye, spinning round the rotor into the volute case that we see here, and passing it down, having provided it with a great deal of increased pressure down into the outlet flow just here. The only other thing I probably want you to see on the fuel pump is this structure just here. This is sometimes incorrectly identified as a governor. It is not. This is a simple safety switch. This is in fact the only direct electrical connection to the turbo pump, and it is designed entirely to detect the revolutions per minute of the pump, and when they exceed 5,000 it closes a relay that actually cuts off the steam supply permanently to the turbo pump. We're going to look at this in a bit more detail, but probably not to the second half of this video, part 2. So look out for that a bit later on. Let's just put the liquid oxygen pump in place here as well. Not connected to the same shaft, but connected to a flexible joint here. Nevertheless, the shaft runs through both pumps, and it is in principle it's the same shaft that's running through the turbine there. Once again, we can see the pump impeller marked out in red this time. The variation in shape of the section through the volute case here. Fuel and liquid oxygen starts at the top, is pulled through into the pumps, into the eye of both pumps, and then passed through to the outlet flanges at the bottom here, and then directly on into the pipework that will carry it into the thrust chamber. Without further ado, let's get a look, before we move on and look at the pump proper in detail, let's just get a view of where the turbo pump is actually located on the missile. If the V2 ballistic missile could be said to have a beating heart, it would certainly be the turbo pump. The steam turbine powered pumps used to drive the propellants into the thrust chamber are certainly one of a handful of enabling technologies that made the ballistic missile a functional possibility. Even today, with large liquid fuel rocket engines, the turbo pump is the critical technology that enables them to function. The location of the pump is relatively easy to find. We can see it situated immediately above the thrust chamber and below the first of the propellant tanks. The tanks here, this is the fuel tank, this is the liquid oxidizer tank, the liquid oxygen, and the turbine powered pump system is immediately below the liquid oxygen tank, and you can see it here, very easy to find as a landmark, where the fins meet the body of the missile. Draw a line across where that is, and that's pretty much where you can find the turbo pump on the V2. So even if you're looking just on the outside of the missile, that's a fairly easy location to find where the turbo pump is actually doing its business. Let's look at another model here. This is my soda can model. It's getting a little bit bashed about now, but I'm just going to take it to bits for you for a moment, again to show the idea of where the turbo pump is located. Let's just take off all the bits and pieces, like the exhaust pipe system and the heat recovery system and the return pipe here. And if I take off this entire assembly, so we've got the thrust chamber. This is a very stylized model, by the way. This is not a scale perfect replica, but it's a didactic model just to be able to show you where the parts are. And if I take off this rather peculiar looking assembly at the top here, this is actually the system responsible for generating the steam to drive the turbo pump. So let's take that off and have a look at that separately. And then we've got the turbo pump. So here we've got the system broken down really into its critical components. We've got the tanking, we've got the thrust chamber, and then we've got the turbine driven pump system, and then the steam drive system for the turbine. These are the two items we're going to talk about today, the turbo pump and the steam drive system. These other items will wait for another video perhaps later on. Looking at the missile itself, now that we've got an idea of where the turbo pump is actually situated, what about if we're not looking at a missile that's got a nice clear side to it? Is there anything we can see on the outside of the missile that tells us something about the turbo pump? We can definitely see something on the outside of the missile that gives us a clue to the action of the turbo pump, and that's in the form of the exhaust vents. And if I spin it round to 1 and 2, fins 1 and 2 here, we can see the vent built into the body of the missile, and this actually receives two pipes on the inside of the missile. There's one coming from the turbo pump, and the steam exhaust actually comes out of here and is quite distinctive on footage taken at the time of test launches. So it's quite a good way of being able to orientate the missile and give you an idea of where it's going. And there is also the liquid oxygen tank also vents to this exhaust port as well. If we go round and look at the fins between 2 and 3, we can see the 5-way connection point used for connecting the missile to the ground station. If we go round a bit further between 3 and 4, we find another steam exhaust port, very similar to the one we were looking at earlier, only this time only steam comes from this exhaust vent. In fact, that's not entirely true. There is oxygen issuing from this vent, but it's coming from the steam drive system and not the liquid oxygen tank. You'll see why later. Now, the useful thing about these vents, and the one between fins 3 and 4 in particular, is that they are handy in analysing the function of the turbopump in test launches and understanding where the missile should be heading. No matter how bad the film footage of a launch is, we can usually see the steam vent, shown here, and the stream of exhaust steam blowing down from the vent like a miniature version of the thrust jet, only more susceptible to the effects of winds, at least in the first few seconds of flight anyway. Now, from the simple fact that we know the missile was designed to lean over in the direction of fin number 1, and that no photographer who wasn't completely crazy would allow the V2 to fly over their head, we know that the pitch program will only take the missile either away from the camera or to the left or right of the frame. It follows from the position of the vent that this must be fin number 3. And that means this must be fin number 2, with the fin on the right being fin number 4. Fin number 1 is the furthest away from us, and despite how it looks from the angle of the missile, is in the direction that the missile will be travelling in after a couple more seconds when the pitch program guides the missile into a ballistic trajectory. Finally, if we go round to 1 and 4, we'll find the liquid oxygen top-up valve. Anyway, so there are things on the outside of the missile that can give you a clue to the functioning of the turbo pump, and in fact in part 2 we're going to look at that in a bit more detail. Okay, so we've looked at the turbo pump in terms of its gross details of its structure. We've looked at the location of the turbo pump in the context of the whole missile, and we've got a clue as to some of the other parts we're going to be looking at in the video. Let's put our models to one side for the time being and actually go to a place responsible for the development of the V2's steam turbine powered propellant feed system and look at a genuine original V2 turbo pump in rather more detail.
We've come to the Peenemünde Historical Technical Museum, where they've kindly let me monopolise their V2 turbo pump so that I can show it to you. It's an excellent presentation showing the complete assembly cut open so we can see what's going on inside. So let's get an overview of the layout of the turbo pump. One of the first things that's clear is the physical size of the pump. It really does impress as a chunky piece of engineering when you see it like this. This is a turbine and dual pump system, so we've got two centrifugal pumps here. On this side of the steam turbine we have the alcohol pump impeller, and on this side of the turbine wheel we've got the liquid oxygen pump. To the usual position, the assembly is upside down, so these supports here are usually the other way up, at least for launch. These are the outflow ports, the high pressure outlet side of the pump, and the low pressure or inlet side of the pump is actually down here. Other features you can see here is the steam exhaust outlet. The spent steam is sent through here where it passes to the heat exchange system and then is dumped overboard via two exhaust pipes. We can see the location and part of the casing of where the overspeed switch device would be located. It's actually missing on this example. This is a mechanism whose sole purpose is to shut the turbo pump down permanently if it reaches 5,000 RPM, and so prevent premature loss of the missile due to the turbo pump overspeeding and destroying itself and the missile. Other things to note: the large steam turbine rotor here is a Curtiss two-stage impulse type. The gas buckets or blades that capture the steam are two different sizes. The row of buckets nearest the steam nozzles are slightly shorter than the buckets furthest from the nozzles, reflecting the way the gas expands as it passes from the nozzles and does its work through the two rows of buckets. The steam arrives via the inlet distributor here, which is constructed of cast and welded parts attached to the oxygen side of the pump. The steam passes into the steam nozzle distribution manifold through these two pipes. The gas is then free to pass around the turbine rotor and through these nozzles that we see here. We've got one set of cast iron nozzles here, another one running down here, and two sets at the back there, 4 in total. The steam is distributed all round the rotor, and it gives you a clue as to the volume and energy in that steam, that it can be distributed over this area and turn this peaceful looking machine into a screaming 600 horsepower monster. So there's a lot of energy in this steam pressure that's hitting the turbine rotor. The rotor turns in this direction. We can see the direct effect that has on the pump impellers. The shaft is not actually continuous. The turbine rotor and the alcohol pump impeller is on one shaft. And then there's a flexible joint on the other side of the turbine rotor connecting another short shaft going through to the liquid oxygen impeller. So 2 shafts, even though they function as a single shaft. This was done to simplify construction and improve stability. We can see the faceplate here of the liquid oxygen side of the pump. And another important feature is the volute case shape, which can be seen from the outside here. We can see the change in the cross-sectional area of the interior of the pump casting. Actually, I think it'll be easier to show you this important structural form of the pump casings from a drawing. So here's a drawing of the ASTOF, or liquid oxygen pump, from 1942. And you can easily see here the spiral shape of the volute case as it heads down towards the discharge flange here. It will be easier to see if I colorise the space. And you can see now how the cross-sectional area increases. Remember, the liquid oxygen, or fuel, is the same for both pumps, is coming in at the inlet port at the top here. The propellant is then pulled into the eye of the impeller, this round area that you can see here, and centrifugal forces are turned into kinetic energy, throwing the propellant outwards radially from the centre of the impeller, where it moves through the smoothly expanding volute case, reducing in velocity but greatly increasing in pressure as it flows down towards the discharge pipe. Now you can see the lack of symmetry in the cross-sectional area of the volute space in the drawing on the left side of your screen. In fact, it'll be easier to see if I switch to another drawing. This is a cutaway through the BSTOF, or alcohol side of the pump, and you can see here we've got the centrifugal impeller and the spaces. In fact, I've coloured the impeller so that you can see that. So the part outlined in red is the part that's spinning, the impeller. And if I colorise the volute spaces here as well, top and bottom here, you can see the difference in the cross-sectional shape easily. The cross-sectional area increases in the direction of the outflow pipe, reducing the velocity of the propellant but greatly increasing its pressure, providing in its transit through the pump the high level of force needed to drive the propellants into the combustion space through the 1,000 of injector orifices in the V2 thrust chamber. I'm just going to show you the pump kind of running, as one of the great things about this exhibit that I can get my hands on it and show you as though it's running, albeit rather slowly. The steam entering through the nozzles here would be driving the turbine rotor in this direction. We can see the steam buckets here very clearly. The alcohol, at a little above a tank pressure of 1 atmosphere, would be picked up at the eye of the impeller here, where, spinning at around 4,000 RPM, powerful centrifugal forces would throw the fuel outwards through the shrouded braids of the pump impeller here, driving it into the spiral shape of the volute case. Centrifugal forces here being turned into kinetic energy and converted into increased pressure by a factor of more than 10, and driving the fuel from the outlet port here into the thousands of orifices and apertures in the combustion chamber. I think after nearly 80 years, it probably deserves a spot of oil. Another couple of things to note here. You can see these bronze-coloured bearing surface savers here, mounted in the faceplate and in the main body. These are large bearing cum seals and are lubricated by the alcohol being pumped. We can see the conventional sealed ball bearing here and another larger ball bearing here. It's worth noting that the bearings in the liquid oxygen pump are of a simpler journal type and are lubricated by the liquid oxygen that's being pumped. Though not complete, we can see some seals and packing pieces here. It was vitally important to keep these systems fully isolated from one another and not allow the fuel or liquid oxygen to come into contact with the superheated steam from the turbine, or worse still, allow the liquid oxygen to party with the fuel, as a rapid, unscheduled disassembly of the turbo pump tends to follow. So, a lot of care taken here to keep both propellants away from the steam turbine casing. Let's have a quick close-up look at that important overboard dump pathway. Fuel, or on the other side liquid oxygen, used for buffering and lubrication and building up in the low pressure cavity here, is allowed to pass out of the pump case and be dumped overboard. There's no flow restriction here, so if needed, flow can increase up to the limit set by the passage diameter. So to round off, let's take a look at some of the marks and stamps we found on the turbo pump.
How do we get from say C, B, B?
A lot of the stampings are numbers. Some are part codes, others are batch run numbers, and some, typically just a pair of numbers or a letter, are used as quality control references to identify assembly personnel and techniques. More interestingly, some parts display three-letter codes. The system of secret three-letter armament codes allows us to identify the primary companies involved in manufacturing the turbo pump, as well as firms contracted to them to make specific parts. This is the liquid oxygen pump impeller, showing EBB for Klein, Schanzlin and Becker AG of Frankenthal, a manufacturer of pumps and the prime contractor for the V2 turbo pump, and still trading worldwide. Turbine casing, also showing EBB for KSB. The steam distributor casing, again showing EBB. The liquid oxygen inlet throat blanking plate, also showing EBB for KSB. This is the steam manifold connection flange, marked OVM, for A. Rieber GmbH Tube and Welding Works of Reutlingen, a maker of commercial kitchen appliances and still trading today. This is the alcohol fuel pump faceplate, showing the letters JUS, unusually in capitals this time, for Weltner Light Metal Foundry GmbH, actually a contractor to KSB supplying aluminium castings, and conveniently dated 18th of October 1943, the last number just telling us how many castings have been run from the pattern. This is the alcohol fuel pump impeller, and at first we see a serial number scratched out for some reason. If we rotate the impeller counterclockwise a bit, we see a new serial number, and rotating the impeller again reveals a three-letter code and some WAFNAMP number quality control stamps. The letters here are ETF for Maschinenbau AG Balke, Frankenthal, a manufacturer of pumps and pump parts, as here working as a contractor to KSB. Of course, other examples of the turbo pump, like this relic of an oxygen pump from early 1945, might display quite different three-letter codes from alternative contractors, even if the primary contractors, KSB or later Mebag, are unchanged. For example, this inlet throat blanking cap is marked GMS, and I've examined well over 20 steam manifold inlet flanges, and so far this is still the only one marked OVM for the Rieber Tube and Welding Works that I've seen.
Let's just take a breath for a moment and just think this through and make sure we're all on the same page and see this a bit more as a problem and how the turbo pump solves our problem. If you've got this far, you've been looking at the turbo pump, a couple of things might begin to creep into your mind, that maybe this is a technology of yesteryear, of the time before smartphones, and that really we don't need to do it this way anymore. If you know a bit more about it, you're probably aware that things like the Redstone missile here, the V2 Mark II, still had turbo pumps, and of course we're still getting into orbit today with liquid fuel rocket engines that have got turbo pumps, sometimes even with this type of steam generator, and sometimes with the steam or the gas used to power the turbo pump coming from the main combustion chamber. So why? What is it about this puzzle that can only be solved by using this incredibly fragile and complex system of the turbo pump and its steam generation system. After all, the problem looks quite simple. We've got our propellant in the tanks here. This is my soda can model that we're looking at here. We've got our fuel at the top, we've got our liquid oxidizer, and we've got on the V2 we've got about 8 tons of this propellant. We've got to drop that propellant into the thrust chamber here in about a minute. If we're going to burn enough of it to hurl the whole missile 200 miles, we've got to get all of that 8 tons in here in around about a minute. Well, surely, if we just take this to bits, let's get rid of this incredibly complicated gas generator here. Let's put that to one side. Let's take off this 600 horsepower whirling devil of a turbo pump with all the risks that we run of it ruining our missile if it goes wrong. If you look at the early tests of the V2, very often a turbo pump underrun or a problem with the gas generator, very common in the figures for failure. So let's get rid of that. How much better our missile is going to be. Now, here we are with the thrust chamber. We've got our fuel inlets down here with the large fuel inlet hole just here. For the liquid oxygen, we've got another big one over here, and then these white pipes going to the burners. This is a very simplified, stylized version of the V2 combustion chamber, thrust chamber. Now we've got our liquid oxygen tank. We can see we've got nice big outlets on that. We just simply match them up with the outlets on the thrust chamber. Missing slightly there that goes. And then we've got our fuel tank here. There's a pipe running all the way down into the fuel inlet of the thrust chamber. And then put my tank on the top here. And there we go. We're ready to roll. We've got our propellant all lined up with the thrust chamber. All I've got to do now is put a couple of valves here, open them up, drop the propellant into the combustion chamber. Well, I guess if those holes were big enough and it just fell through, we probably could empty these, providing it was well enough vented at the rear end here. We probably could drop that stuff in there in around about a minute. But there's a problem, and the problem is these thousands of apertures that this propellant has got to go into to make our jets and to form the nebula that is going to be burnt actually inside the combustion chamber. And you can kind of picture that in your mind, how difficult that would be. Imagine you've got a length of garden hose and you've put your lawn sprinkler on one end, but instead of connecting it to the tap, you just put a funnel in it and you start pouring water in out of a bottle or out of a bucket. I think you can picture fairly easily that once the pipe filled up and the water starts to dribble out the other end, you're going to be, the rate limiting step is the rate at which it's dribbling out the other end. You're actually going to be metering in the water relatively slowly here as it drains through that system, because it hasn't got the pressure of the tap and it's not going to force the water out the other end into a nice jet, not unless you put that funnel and the pipe way up in the air anyway. So we've got our propellant at roughly 1 atmosphere, and with a little bit of a drop, I think it would take about 20 minutes to go through all those nozzles, possibly even longer, rather than the 1 minute that we need for our burn. Well, okay, that's pretty easy to fix. Why don't we just take compressed nitrogen or compressed air? These things are pretty common. And why don't we just pump the air directly into the tanks? We can easily meter the amount of nitrogen that we're going to pump out of a compressed tank like this, and we should be able to get that pressure consistent all the way through the trajectory, at least for the length of the burn, and get the right kind of 10 atmospheres that we need. Don't forget, we need quite a bit of pressure, because not only we've got all those nozzles, we've got the fiery furnace there, the combustion chamber burning and creating a lot of pressure inside the combustion chamber, pushing back at it. So really there's a lot going on in there to stop the propellant getting into the combustion chamber. But we should be able to fix that. So really, what's the problem? How come there's a fat Englishman on YouTube that can solve something that the Germans, all these smart engineers, couldn't solve all those years ago? First of all, I'm going to need my Meccano on a roll. Elon Musk, eat your heart out. I don't know why you didn't think of using this stuff to cut your costs. few bits of this. So here it is. Looks a bit odd with the tanks in tandem like this rather than in single file, one behind the other. But in principle, you've got everything you need here. We've got our thrust chamber down the bottom. We've got our piping, our pipe going to the fuel tank and a pipe going to the liquid oxygen. And we've got two valves here, which I can operate by just squeezing them together. A couple of electric valves here, a few other bits and pieces, and we've done away with the turbo pump completely. We've got a nice simple system that just needs a bit of piping and a couple of valves. How much better that would have been than this very complicated system here. So let's hear it for the fat Englishman who had a much better idea than all those clever Germans all those years ago. Well, come on, think about it for a moment. There's a problem here. And you can kind of see it if you look at these tanks. Look at the soda can tanks on the model here, and they're actually a pretty good scale modelling of the tanks from the original V2. They really, if you scaled the tanks of the V2 down to this side, they really would be as incredibly thin as a soda can, soft like this. Now look at the tanks on the gas propellant system. They're made of steel. All these seams here are steel. This is all soldered together. These are very tough, thick tanks. These are made of very heavy metal. Now there's a crossover point. If we think about the missiles that were being made 80 years ago that predated the V2 or even made at the same time like the A5, all of those missiles up to the A5 used this gas pressurization system rather than a turbo pump. But there's a crossover. There comes a part on the graph if you plot the thrust and range of the missile and whether you can get away with this system, and there's a cutoff point where if the missile goes over a certain size, you just can't use this system anymore. You've got to go with something that is a lot lighter. Otherwise, you're going to completely hobble your missile in terms of its range and its carrying capacity, because quite simply, the tanks end up heavier than the turbo pump. And this happens simply because as the size goes up, the amount of bracing and support and extra metal that's got to be piled in to make those tanks be strong enough to be able to take the pressure dramatically increases, to the point, as I say, where on a missile the size of the V2, the tanks are going to be a lot heavier than the turbo pump system. So the logic behind using the turbo pump is still overwhelming. So when you look at liquid fuel motors today, you're still going to be seeing this turbo pump technology reigning supreme for anything other than a very small missile. Now, before we go back to the engineering, I just want to expand on one of the points that came up at the end of that presentation at the Peenemünde Technical Museum about the role of commercial contractors, not just in the supply chain supplying parts and assemblies, but actually in the development history of the turbo pump.
In the mid-1930s, when the Army missile team were first getting to grips with the idea of using high-performance pumps rather than a gas feed system that we were looking at a moment ago, someone in the group drew their attention to the flow and pressure performance already available in firefighting water pumps. And this set them on a mission to talk to people with commercial expertise in this area. Although the final mass production of the turbo pump involved other companies, Wumag of Görlitz, Heinkel of Jenbeck and later Mabag of Nordhausen, the crucial work of the development was entrusted to industrial pump experts at the southwest German company of Klein, Schanzlin and Becker, or KSB for short. We know from historical documents that the project to develop the V2 turbopump began as early as 1935. This document, written by the technical leader of the missile program, Werner von Braun, is a progress report to his masters in Berlin, and it details new projects underway or expected to be in the current year. The report is dated 1935, and point number 7 refers specifically to a project already begun to develop a centrifugal propellant pump with commercial partner Klein, Schanzlin and Becker.
Kreiselpumpen für Brennstoff und Flüssigsauerstoff in Zusammenarbeit mit Klein, Schanzlin und Becker.
Founded by Johannes Klein in 1871, by 1916 KSB's factory site in Frankenthal was one of the biggest in Germany, covering over 60,000 square metres and employing over 4,000 people. KSB had a good record of pump innovation and owned a number of valuable domestic and foreign patents pertinent to the pumping industry. By 1930 they were one of the most prominent pump designers and manufacturers in the world. This drawing, for the turbopump design, is dated 1937 and shows that initially at least, the pump development group at Peenemünde seemed to have been communicating with the people at Maschinenfabrik Odessa GmbH. The Odessa company, who are still trading by the way, was acquired by Klein, Schanzlin and Becker in 1929, and from 1939 the company was known officially as Klein Schanzlin Odessa GmbH, a wholly owned subsidiary of KSB. We can see in this drawing from the 1st of October 1940 that a lot of work has been done since 1937, and the design of the pump is starting to look a bit more familiar, with details like the general location of the inlet and outlet flanges and the design and position of the steam inlet, shown here in red, and the steam exhaust port here. But the outlet flanges are still not in line with the inlet flanges and are positioned in line with each other but off to one side, and the mounting brackets are shown at the cardinal points, one on each end of the pump and 2 either side of the turbine casing. This rare but poor quality movie clip, shot in Peenemünde sometime in 1940 to 41, shows a turbopump variation indicative of the late 1940 development period seen in the drawings. In fact, most of the features we've just been looking at are here: the off-center outflow on the right, mounting brackets at cardinal points, and the non-360 degree steam manifold. By the end of October, the exhaust port throat area has been enlarged, and they are trialling the steam input manifold in a new location adjacent to the fuel pump, and dangerously close. But the outlet flanges are still level and off to one side, and the mounting brackets on the turbine case are more robust, but all 4 are still at the cardinal point position. Oh, and right down the bottom there, they've finally spotted the spelling error. Good lads. This drawing, from June 1941, looks almost like a production series turbopump and very similar to the pump we showed you earlier. The steam inlet has arrived in its final position and stood off 250mm from the steam nozzle array and positioned outboard of the liquid oxygen pump case. Critically, the outlet flanges are now in line with the inlets and no longer level. The mounting brackets are settled, larger and located only at the horizontal positions, integrated into the castings either side of the pump volute cases. At the bottom right there, Odessa is still formally identified as the supplier. This long-running misidentification was finally corrected 3 months later in November 1941, with this almost identical drawing showing more refinements to the internal diameters of the inlet and outlet apertures and changes to the overspeed switch area. And down at the bottom there, KSB, or Klein, Schanzlin and Becker, is now identified as the primary contractor. Now, just to put the last drawings and the next into a wider context, the first but unsuccessful A4 flight test model was completed 25th of February 1942. This undated clip shows an A4 missile being assembled in Peenemünde sometime towards the end of 1941 or the first weeks of 1942. In this drawing, originating from the first quarter of 1942, we see an almost production series system and the pattern for the turbopump that probably flew on the first successful launch of the V2 on the 3rd of October 1942. It's still not quite the 1943 machine I presented from Peenemünde earlier, but it's getting close. The inlet throat shape and the fuel loopback areas have yet to be finalised, but the first ring of the steam inlet manifold is a full 360 degrees now, rather than the 200 degrees of the earlier versions. And the overspeed switch assembly and its location has now settled into something resembling the production series pan. Interestingly, if we look at the data panel here, showing the dates and drawing numbers, it's worth noting that the first two names responsible for this drawing are the same names that appear on all but the first oldest drawing we've shown you. We'll close this section with a memorable endorsement of the turbopump development contractor by Peenemunde's technical production manager Arthur Rudolph. In 1989, responding to questions from space historian Dr. Michael Neufeld, Rudolph stated, "We hired Klein, Shanslin and Becker to do this development, and they did marvellously, really marvellously." Later on, when discussing the V2 missile project as a whole, Rudolph drew attention jointly to KSB and guidance specialist Kieselgeräte GmbH, stating that these were the outstanding contributors.
Now obviously that's just a sample of some of the communications between the pump experts at Klein, Shanslin Becker, KSB, and the turbopump technicians at Peenemunde. There's obviously a fantastic amount of detail that could be piled in there in the design and development work from its inception in 1935 through to the first drawings that we saw there in 1937, all the way through to the first successful flight of the V2 in late 1942. A huge amount of effort was made to develop this absolutely crucial part of the V2's liquid propellant rocket engine system. In fact, you would probably say that the turbopump is the critical technology in making that motor system successful. I want to go back to the engineering of the turbopump now and cover one of the points I think that was in the air in that presentation that I showed you from Peenemunde when we were looking at the relic turbopump from I think 1943. I spoke a lot about the hardware of the turbine and the use of superheated steam. That came up a lot, but I didn't talk at all about how the superheated steam is made and where it actually comes from in doing its job of driving the turbine. So we rather left that out. Let's deal with that issue right now and look at how the superheated steam was actually manufactured that drives the V2's turbopump.
We're at the Deutsche Technikmuseum in Berlin, where they have a very accessible V2 engine, turbopump, propellant tanks, and more importantly, a well-displayed steam generation plant. It's incomplete, but that's not a problem for our current purposes. We'll be returning to this excellent exhibit in this and other videos. So let's look at where this powerful jet of superheated steam that powers the turbine part of the turbopump actually comes from and how it's made.
This is a full-size model of the Walter steam generation plant used on the V2 missile. The superheated steam that powered the gas turbine was generated in this combustion chamber. The steam passed through this steel pipe, lagged with asbestos here, and on to the turbine of the turbopump. To make this demonstration model showing just the essential elements of the steam plant, we've actually used a small number of original relics from the V2 steam plant, like the main valve here, the 25-ton valve, the sodium permanganate tank, and the contact switch, as well as recreations like the gas generator pot and turbine connection pipe. We've also used new parts to complete the model, like the piping here. The air and flow control valves up here are modern. These valves won't be discussed much in this video, but they do feature in another video we have planned about the J-Geräte, or J device, the integrating accelerometer used to determine the range of the missile. We're going to look at the demon in the machine, the monopropellant chemistry that lies at the heart of the Walter steam generation plant in a moment. But first, let's get a helicopter view of the main hardware components of the system. So the basic fuel used in the steam generator is high-strength hydrogen peroxide, or H2O2. Yep, the same stuff used to whiten teeth and bleach hair, only in a vastly more concentrated form. It's carried in a pressure tank above the steam generator.
We can see the ellipsoidal-shaped hydrogen peroxide tank in this museum exhibit. The yellow H2O2 container looks like a giant American football or a rugby ball, and we can see the large diameter pipe carrying the H2O2 down to the 25-ton valve, seen here in cutaway, revealing its internal parts.
And here's that same pipe carrying the hydrogen peroxide down to the 25-ton valve here. Okay, let's just hold it there for a bit. We're going to come back in a moment and we'll take a look inside some of these key components and see what's actually going on inside there. But first, let's look at the stuff that is actually flowing through this plumbing and get ourselves a little bit more familiar with the surprisingly simple monopropellant chemistry that generates this steam that passes through this pipe and onto the turbine and turns that nearly 20-inch turbine wheel at speeds of up to 5,000 revolutions per minute. Before we look at the steam plant for the V2 turbo pump in any more detail, let's just try to get a basic understanding of the essential principles and chemistry used in the Helmer-Walter steam generation plant. To do that, we're going to do a little demonstration outside rather than in here, using some bits and pieces that we put together. The original steam plant system for the V2 used high strength hydrogen peroxide, H2O2, to an 80% strength, a very dangerous product. We're not going to have any truck with that at all. We're going to be using 35% strength hydrogen peroxide, and we're going to be using potassium permanganate crystals. So we're going to use the potential, the energy potential of these two products basically we're going to use the energy potential of this product, hydrogen peroxide, and we're going to liberate that energy using a catalyst, the potassium permanganate. The Germans would have used sodium permanganate to do this, but the technical literature does often mention that they used potassium permanganate. I'm really not qualified to say whether that's true or not, because I can't quite understand why they would, because potassium permanganate I don't think takes up water as well as the sodium. Although the products are virtually identical in the way that they would work as a catalyst for the hydrogen peroxide, the slurry, the suspension that would be made up with the sodium permanganate, I think would be a lot more efficient than potassium permanganate. Anyway, that's what we're going to use. Potassium permanganate. You've almost certainly encountered it before. In fact, you've probably even tasted the stuff. When you've been at the dentist and you've had a filling done and you've heard those words, rinse out please, it's exactly the same stuff. Lower dilutions than we're using it here, of course, but potassium permanganate, it's exactly the same stuff. Cheers. We're going to need a little bit more apparatus, so let's just look at that. Well, the first and most important part of our demonstration apparatus is this dual pump and turbine. This is a single shaft with two centrifugal pumps on board. This is the genuine article. This is from an S-75 Dvina Soviet surface-to-air missile. The Saev Design Bureau that came up with this little item had the V2 missile and the German Wasserfall missile very much in mind, and from our point of view it's quite a good mini analogue for the turbine rotor and pump rotors for the V2. It's quite a bit smaller obviously than the V2 system. The turbine wheel here is around 8 inches in diameter. The V2 was twice the size of that, over twice the size in fact. And there's nothing to be learnt by looking at the design of this rotor, because the German system was completely different. I'm going to show you that in just a bit. What I want you to get from this is just the general design of it. The German system was regarded as a single shaft turbo pump, but in fact it had a broken shaft, so the fuel and the rotor in fact, I need to turn it around. This is the fuel side. So the fuel and steam turbine was on one shaft. There was then a soft joint that enabled the oxidizer shaft to be butted on. But in principle, what it meant, there was no gearing or anything else in the way. It meant that a single rotation of the turbine equaled exactly a single rotation of the pump rotors on either side of it. Rather different to the V2 are the varying size of the oxidizer here and the fuel pump on this side. You'll notice that the fuel pump is a bit smaller on this system. We see the eye in the center here where the fuel goes in, and we've got a nice shrouded pump rotor, centrifugal pump rotor here. But if we look on the other side for the oxidizer, we can see that it's a larger diameter. So this would have a different dynamic when supplying the oxidizer, which incidentally wouldn't have been liquid oxygen on this type of missile, because the missile needs to be ready for instant firing. This would have used a non-cryogenic oxidizer like fuming red nitric acid. Same design though. We've got the fuel, the oxidizer is taking in the eye and then sent down into the combustion chamber. One of the little things to note here is that the side where I'm going to be shooting the gas, you can see it's slightly smaller. So the gateway and in the rotor blades here is a little bit less than the gateway on the other side, and you can see that the rotor, the turbine rotor, has got this rather nice kind of cant on it to reflect the fact that the gateway is slightly smaller on this side, and as the gas expands through on the outside, hopefully you might be able to see that when we do the demonstration. Anyway, we've made up a little rig here to hold this. I've just got to put the bearings in the right position, and that brings us on to the next most important part, and that's the gas generator itself, the gas pot, sometimes referred to as the disintegrator by the Germans and in the on drawings and in literature. What I'm using is a plastic bottle. This is actually a plastic pressure bottle from a popular home carbonated drinks system. So basically you would plug this into one of these gadgets where you pull a lever down and it would pump carbon dioxide into the beverage of your choice to make a fizzy drink. I've chosen this because it's quite a tough bottle. It's made of very thick material, and it's got these kind of this nice kind of pressure body shape, and everything is very tough, and I'm going to be able to do stuff up very tightly with it. I've turned the lid into a steam nozzle, and I'm going to bolt the base, screw that down onto the wooden platform here so that I can put the bottle into position and put it at a good angle to put steam onto the rotor buckets here. Then I'm going to supply the hydrogen peroxide from this little simple dispenser. What I've got here is a little tip which I'm going to drill into. I'm going to drill a hole in here, and I'm going to glue this into position into a hole in the side of the my gas bottle here, and you can see that the hole in the tip there is only about 1.5 millimeters in diameter, so that I get a very modest flow here by just squeezing the bottle. The feed pipe goes all the way to the bottom, and I can control the amount of hydrogen peroxide by just varying the amount of pressure I put on the bottle. I'm doing that because I really don't want to get myself showered in hot fluid from this system, and I want to be able to control the amount of pressure. So I've got a fairly generous sized nozzle. This is about 7-8 mil in diameter, this piece of copper pipe, because I don't want too much pressure actually building up inside here. It may only be 35% hydrogen peroxide, but it's still got more than enough energy to blow this bottle apart, I think, and I really don't want any accidents. We've done some tests with this combination of materials just to make sure this will work, but we haven't actually tried this out yet. So that'll be you'll be with us when we do that outside, but I am reasonably sure from the tests we've done that what we're doing here is quite safe and straightforward. Now hold that thought just for a second. Let's just pause and take a breath, partly for light relief, but also to remind ourselves of an important watchword in the history and development of the liquid-fueled A4 V2 missile, and that word is testing. Test and test again. So by way of light relief, just have a look at one of the tests that we did to test the strength of the 35% hydrogen peroxide and the potassium permanganate that we were going to use to power this test over here. Take a look at this.
I squirted that in there and it just went whoosh! You know, mental. Mental.
Away we go.
There you go. Pretty energetic, one way and another.
I'm going to introduce the squirt of potassium permanganate now. There she blows.
So what's going to happen is I'm going to mix the potassium permanganate with water. I'm not going to use too much water. I'm going to put a charge of about 50 millilitres of water, and I'm going to add as much of these crystals as I can, so that the water will take up most of it. Let's just show you this, and form a suspension and a slurry with the material. I'm probably going to put more in it than I think the water can take up, because I want to make sure that the water is as saturated by the KMNO4 as I possibly can. And I'm then, once I've got it sitting in the bottle here, and that pretty well mimics what the Germans were doing. The Germans made sure that the sodium permanganate that they were using arrived in this tank first. They then continued to meter a slurry of sodium permanganate into the gas flask throughout the burn process. So for upwards up to about 70 seconds, they carried on feeding sodium permanganate into the steam generator bottle until the end of the burn. And obviously they continued supplying a liberal quantity of high-strength hydrogen peroxide into the bottle as well. Anyway, without further ado, let's take it all outside and make it go. Apparatus that we need. So the equipment's pretty much ready. We just take off the lid and gas jet from the combustion chamber, and I load in the potassium permanganate catalyst. I've got about 100 millilitres of this mixed up, and I've put quite a bit of permanganate in there. In fact, I've got as much in as I think the water can take up, and there's quite a bit of sediment in there, so it's pretty much a thick slurry. Get the jet nozzle lined up again. I'm a little bit concerned that it's a bit too far away from the turbine wheel, but we'll go ahead anyway. Fill the applicator up with hydrogen peroxide. Being a bit sparing with this, making sure I've got enough to go for a few tests, just in case this first one doesn't come off. I've put enough in there to give us a few puffs to get this going. A small quantity of hydrogen peroxide. Now these videos are meant to be a laugh, but I'm not Harold Lloyd, so safety first. So we're ready to go. First try. Nice quick reaction, but a bit feeble. Also, you'll notice that the bottle is starting to distort and the nozzle is starting to creep away from the wheel because of the heat being built up in there. So I think we need to get the nozzle in closer and maybe make the nozzle in the hydrogen peroxide applicator a bit bigger to get a bit more H2O2 in there. So let's try again. Okay, well that's better. It's not really going very fast, but good enough to make the point, I think. The nozzle's still creeping away in the heat. Try it again, a bit closer, another run. Quite a bit of fluid coming up on there, but makes the point, I think. Once more, very close, just to see what's happening right up against the rotor buckets. You can see there's quite a bit of this dirty fluid with spent catalyst in it. Well, we didn't destroy the apparatus by getting it too hot. I think if we'd have been able to get more hydrogen peroxide in there other than through my little jet, we could have probably got the RPM up. The snag is it would have destroyed my plastic bottle and it wouldn't have been quite so visible what we were doing. So all in all, I think that was quite good. One thing that did surprise me was how the extent to which the catalytic potential of the the potassium permanganate didn't actually degrade with all the water that was being put in. It seemed to carry on. I seemed to be getting roughly the same amount of energy every time I gave it a, it still works even now, every time I give it a puff of hydrogen peroxide, it sort of carries on working and get roughly the same amount of steam, perhaps not quite as good, every time I give it a puff. Anyway, that's that. Well, we've washed up the equipment, so let's have a wash up and see what we can actually carry away from this little demonstration. Well, some of the equipment didn't fare too well. Our gas bottle here, the gas generator, took quite a bit of punishment and ended up being quite badly distorted, but I guess it held together well enough. In fact, it ended up being quite a bit smaller after the test than it started, which surprised me rather. I knew it was going to buckle a little bit, but I didn't expect it to get uniformly smaller as a result of the heat, but then I suppose it's not that surprising. I guess the main thing we need to carry away from this is the fact of using a monopropellant, the H2O2, the hydrogen peroxide, combined with a catalyst to create an energetic stream of steam under pressure with oxygen. In the case of the 80%, very energetic. Remember, the test that we've shown you is 1,000 times less energetic than the real turbine jet steam pressure would have been. The 80% hydrogen peroxide is a very energetic propellant compared with what we were using here, the 35%. We've shown how that steam pressure can be used to generate the rotary motion of a turbine, which in turn can be used to as the propulsion system of two centrifugal pumps to push the propellant down into the combustion chamber. I think we've established that quite nicely. Along the way, I think we noted almost in passing that the catalyst, in the way that it gets drawn and combined with the hydrogen peroxide, only needs to be supplied in a sufficient quantity. Could easily be to excess, because the H2O2 basically utilizes the catalyst as required. So providing there's enough or more than enough, we don't need to be too particular about the amount of material that's in, and that's probably a good thing on the A4 V2 steam plant, because quite a bit of this catalyst would have been carried away with the steam. You may have noticed in the test that the steam that we were producing was quite wet. This is because it wasn't superheated steam. Remember, the steam coming from the steam generation plant, using the high strength 80% hydrogen peroxide, this would have been superheated dry steam. So we wouldn't have seen all of this wet over the turbine. But it is worth bearing in mind that some of the catalytic slurry would have been carried onto the turbine. And that's probably not a particularly clever idea when you consider the speeds and pressures that we're talking about here. One of the other things that we saw was the angle of the gas jet as presented to the turbine wheel, and that the exhaust jet, the expanding exhaust jet, was moving away at a sharp angle and returned basically to a sharp angle in the opposite direction. Also, we noticed that the exhaust jet was expanding as it moved away from the exhaust side of the turbine rotor. We saw it rather nicely just here. We saw the steam going in at this angle, and we saw the exhaust path of steam coming away at a sharp angle in the opposite direction. We also saw the gradual expansion of the steam as it passed through the rotor bucket gateway. Okay, so let's carry all of those ideas with us as we take a more detailed look at the turbine steam generation plant, the gas jets, and the steam turbine rotor wheel of the actual A4 V2 missile rocket motor. Okay, back with the steam plant hardware again. Let's try to tie all these ideas together into a functional whole. Earlier I said we would look at some of the components of the steam plant in a little bit more detail. Let's kick that off by looking at these crucial valves responsible for releasing the hydrogen peroxide into the gas generator pot. As I showed you earlier, the primary valve in the steam plant that controls the flow of hydrogen peroxide is called the 25-ton valve. The second valve, just above it here, is known as the 8-ton valve, and it also controls the supply of hydrogen peroxide. The 8 and 25-ton valve names are derived from the amount of steam delivered to the turbine, and therefore the amount of rocket engine thrust that is achieved by the effect of these valves. When the 8 and 25-ton valves are open together, the generator produces enough steam to drive the turbine at its rated speed of 3,800 to 4,900 RPM and push enough fuel and liquid oxygen into the engine to produce around 25 tons of rocket thrust at ground level. When only the 8-ton valve is open on its own, the thrust drops by 2/3, not too surprisingly, to a little over 8 tons, hence the name. The most important point to notice at this stage is that both valves are being supplied by the same hydrogen peroxide pipe that connects to the main hydrogen peroxide tank. There are no special extra pipes or anything like that. Both valves are being supplied by the same pipe. It looks a little bit confusing because the outflow on the electric flow valve here, the 8-ton valve, is connecting directly to the air-controlled 25-ton valve here. And both valves are passing hydrogen peroxide into the gas generator tank. This is an important feature of the steam plant, both for this and future episodes, so we'll need to look at this in a little bit more detail.
Here we see the whole steam plant subassembly, with this battery of 7 air or nitrogen bottles attached. The assembly was a surprisingly simple structure, and was secured to the chassis of the V2 with just a handful of bolts. Let's isolate the 25-ton valve from the plumbing so that we can get a better look at it, and then section it so we can see inside. This valve is pneumatic, and we can see the air piston on the left side. A heavy spring keeps the valve normally closed, and the piston is driven down the cylinder to the right by the air, or nitrogen as it's typically specified, at 500 pounds per square inch. The air pressure moving the plunger off its rubber seating to open the valve, allowing H2O2 to flood into the gas generator pot below. At exactly the same time, the 8-ton electric flow valve also opens and allows just over 30% of the total H2O2 to reach the gas generator pot by a bypass route through the same 25-ton valve. The significance of this bypass route becomes apparent when the 25-ton valve is closed, halting the main supply of H2O2 to the gas generator, as now a greatly reduced volume of H2O2 continues to reach the gas pot via the 8-ton valve and bypass route. So even though the primary valve is closed, the turbine keeps running only at around 1/3 its original speed from this reduced supply of H2O2. Less hydrogen peroxide in the gas pot means less steam on the turbine, so fewer revolutions from the pumps and thus less propellant pumped into the rocket engine. Let's take a quick look at what we can learn from a 25-ton valve relic recovered from a launch failure from the 1943-44 era. Made of light alloy and still showing its original anodized colour, it was incomplete when we received it, missing the air piston end cap. I'll just remove the airline connection. The cap here is made of ABS, and I 3D printed it from an original part drawing transcribed by my friend Alexander Savochkin. You saw his drawings earlier. We can see here on the wrecked H2O2 feed pipe the connection point for the 8-ton bypass valve, and here again on the main valve. Let's just unscrew and remove the hydrogen peroxide feed pipe and union so that we can see the valve plunger. You can see it's slotted to aid assembly. The spring was missing, so I fitted a much weaker one so that I can easily press the piston in and show the valve working. Let's just undo the nut holding the makeshift piston and seal to the end of the valve stem. I can remove the valve core or plunger now, all light alloy construction. We can see the stem gas seal down the bottom there, held in by a C-clip, and the valve seat here, which is normally loose like this, and held in place by the H2O2 feed union. It has an integral valve seat made of some form of hard rubber substitute. The valve stem just fits back in there. And we can see a little air relief hole here to relieve pressure on the valve side of the piston. Otherwise it would resist movement if we didn't let the air out. The H2O2 outlet pipe running to the gas pot here is not original. But we can see the high pressure seal here. If we just pull the plunger and seal out again, we can just see the pathway from the bypass connection through to the main H2O2 outlet. Probably easier to see if I poke my pointer in the bypass valve opening and then just flip the valve over and poke it in the main outlet opening. So you can see both holes open into the same cavity. Okay, let's get back to where we were again. When the start or preliminary stage button is pressed, a system of subvalves allows propellant to flow under the action of gravity into the combustion space of the engine, where a simple pyro or firework like a Catherine wheel lights the fuel and oxidizer mix into a steady flame. Even though the V2's rocket engine now begins to run at around 2.5 to 3 tons of thrust, not the 8 tons that you've read about in some books, the steam plant and turbopump remain completely idle. They make no contribution to the running of the V2's rocket engine at this stage. At this point, fuel and liquid oxygen is simply falling out of the tanks and through the static pumps into the thrust chamber's combustion space.
Hauptstufe.
When the main stage or Hauptstufe button is pressed, a valve opens that allows air to pass into the sodium permanganate tank through this pipe and allows the catalyst to begin flowing into the steam pot. But still nothing changes. The rocket sits on the launch stage. The engine is running at about 10% of maximum thrust. But an automatic process has begun that requires no further human intervention. The sodium permanganate continues on down this pipe to this contact switch. Although it has a pipe running to it, this is not a valve, it's just a switch. The fluid pressure pops a diaphragm inside and closes a set of contacts. The switch closes a relay that instantly energizes and opens these two valves, the 25 and 8 ton valves together. So we're now in a position to appreciate what's going on in the secret darkness of the steam generation flask. The sodium permanganate liquid catalyst arrives first, allowing the arrival of the high-strength H2O2, where a violent chemical reaction occurs instantly, reducing the hydrogen peroxide catalytically to superheated steam and oxygen. The steam blasts out of the bottom of the gas pot and is carried by a steel pipe, missing on this exhibit, to the steam inlet flange on the steam distributor of the turbopump, and onwards directly to the steam nozzles to provide power for the turbine rotor. The steam encounters no more valves or any form of hindrance and hits the turbine rotor, which spins the pump impellers, sending fuel and liquid oxygen under greatly increased pressure onto the main thrust chamber valves, opening them by shear force. The fuel and liquid oxygen gains access to the combustion space by forcing the valves open by pressure lent to both propellants by the turbopump. And we have liftoff. The 25 tons of rocket thrust overcomes the 12-ton missile frame and tank weight, and the missile rises at roughly the same speed as a falling object, and continues to do so, and thus attaining great velocity and altitude before the burn ends a little over a minute later. Hold on a second. We need to go back, as we haven't explained why we need these two valves. We've covered that they are both fully open to start the turbine, but why do we need to throttle back from 25 tons of thrust to just 8 tons via that second valve?
Now, the V2's requirement to throttle back immediately before engine shutdown was done to refine the final velocity measurement to improve the range calculation of the missile. Now, it's far too interesting an idea for me to skim over lightly here while we're talking about the steam plant, and we're going to deal with it in a lot more detail in a subsequent video that looks at the gyroscopic accelerometer and how it was used to control those two valves and more precisely control the range of the missile. Anyway, that's in a subsequent video. Don't forget to subscribe if you want to see it.
Let's get back to Alexander Savochkin's drawing again for a moment and look at the steam plant's gas generator part in detail. Let's pull it out of the plumbing again. The H2O2 comes in, as we've seen, from the left here, and a steady flow of catalyst is fed into this smaller union lower down the body of the pot. If we section the pot so that we can see inside, at the bottom of the H2O2 inlet tube we can see a spring-loaded pass valve that ensured that only propellant at the correct pressure could enter the steam pot. And further in, a non-return ball valve in the tip ensured that no matter how violent the reaction in the chamber, nothing could be pushed back into the hydrogen peroxide feed system and cause a malfunction or even an explosion. The catalyst pathway shows a rather more direct and open route. The pot has a number of features designed to allow maximum exposure of the catalyst to the incoming H2O2. The jet of sodium permanganate is designed to spatter on contact with the small round target visible at the base of the funnel we can see surrounding the H2O2 nozzle. A number of baffles separate the area below the funnel from the lower section of the gas pod, and most intriguing of all is the helical helter-skelter slide that passes around the central core. The shape is well shown in this drawing. They were designed to slow down the exit of the sodium permanganate to make sure that it had the best chance of thoroughly catalyzing the H2O2 into the maximum volume of superheated steam.
Okay, let's take a look at the steam rotor of the V2 turbopump, the agent that actually turns this powerful jet of steam into the rotational motion of the pump impellers. Earlier I showed you the steam rotor and pair of combined pump impellers, and I made the point that it was a fairly good analogue, if a somewhat miniature one, for the V2 turbopump hardware, but not a good analogue for the actual design of the rotor itself. And that's because the rotor here on the Asaev steam turbine is stainless steel and made of pressed and welded parts. In contrast, the steam turbine rotor of the A4 V2 turbopump is actually a 45 centimeter machined light alloy wheel with two slots machined into the perimeter of the wheel. A few years ago we shot some footage of a very badly corroded turbopump on display at the Technical Museum in Peenemünde. And though the turbine is in pretty poor condition and quite badly corroded, it does allow us to show you the salient points of it, I think, really rather well. We can see its construction here and its physical size really quite nicely here. But the thing I want you to notice is the type of construction we've got. Here's that slotted rail you can see, and the teeth inserted into it as separate components. It's although it's badly corroded, looks like it's been in water. You can actually see it very clearly down here, the separate rotor blades actually looking like teeth in a jawbone. Got a couple of examples here of the turbine buckets, the turbine blades, that have been converted from original drawings by Lars Osborne, and I was able to print these out in a 3D printer quite easily, and they show a lot of the detail. You can actually look at these yourself on Thingiverse, where this drawing has actually been uploaded. The really good thing about bits like this is that I can actually print them out in an enlarged form. This Land of the Giant version here, which is going to be a lot easier to show you the details, it shows how the rotor blades actually fit together, and it's easy to show how, once we start putting a stack of them together like this, you can actually see a curve starting to form here quite easily, and we get this very distinctive fish scale look to the top of the rotor here, which you'll see in pictures easily enough. You can see if I put them in a line here and put the other ones up against them, you can see there's quite a gap. Even if I squeeze the bottoms together, there's quite a gap at the top, and if I squeeze those together, you can see that they start to form a curve. So they really are very craftily made in that they take up the shape just by squeezing them together without putting them into any kind of a slot. They really are designed to create this curve of the rotor. Now, it's a good illustration of the difficulty that the Germans had rolling the V2 out into a mass production product when we give consideration to this little gadget, the turbine blade or bucket. We've got a really very complicated structure here with something like 7 or 8 machine tool operations being required to make this to a very, very high standard. When you consider that a similar item can be made with just 2 operations, stainless steel cutting and bending, making a very simple but very effective blade. Each turbine required over 460 of these rather complicated little items, and that's pressing towards 3 million for the German rocket program as a whole. And it's pretty easy to see why the mass production project was so difficult to initiate when you've got prototypical products like this that really could and should have been replaced by something much simpler. We can actually use a couple of relics here to investigate the structure of the steam rotor. We can see it, these look like they're fantastically misshapen after the severity of the impact that these steam rotors actually went through at some point in their lifetime. But we can actually see here the inner section of the rotor wheel. We can see its general shape and size, and in particular we can see the 2 rows of rotor buckets here. They're sort of getting ready to actually come out. They've been quite badly damaged, but we can see the difference in height, and we can see how they've been fitted in to the rotor. I think I can show it to you better with this one. It's had a much cleaner brake, and I can fit my 3D printed turbine blades or rotor buckets into there. We'll fit the second one in quite nicely. There's enough room for it. If I push it home, and you can see how they fit in there, but it's all very damaged and buckled. It would be nicer if I could do this on the Land of the Giants version of the rotor wheel. And just by chance, and as they say on Blue Peter, here's one we made earlier. You can see I've put a run of rotor blades in here already, and we'll just put a few more of these in, and you'll see how they fit together rather neatly and take up a nice snug position against one another, fitting together perfectly. And you can see picking up that fish scale look to the top of the rotor buckets here, looking very distinctive in the way that method of construction leaves the steam rotor looking. Now, of course, there was 2 rows of these buckets on the steam rotor.
We saw that the V2 turbo pump had a 2-stage rotor that used 2 separate rows of steam buckets or blades. In contrast to the relative simplicity of a single-stage steam rotor, like the Soviet-era rotor we used in the demonstration, the V2 rotor system needed an essential bit of extra hardware between the 2 rows of rotor blades. Just like a single-stage rotor, the steam jet is directed into the first row of steam blades at the best angle for maximum rotational efficiency of the turbine rotor. But the steam still has a lot of energy that has not been harvested by the first row of blades. So the way to exploit that energy is a second row of blades. The snag here is that the steam jet has been bent well away from the ideal angle by its passage through the first row of blades. The solution is a fixed row of blades in the middle with an identical curve but in the opposite direction, called a stator. The stator blades restore the steam jet to the ideal angle for the second row of blades. We can see one of the turbine stator sets here in the left hand picture, and we can just see the base of one of the stator blades shown in red. This Peenemünde drawing from 1944 identifies the moving rotor blades as A and C, and the fixed stator blade as B. The lower picture shows the angle of the steam nozzles and the switchback nature of the steam path through the blades perfectly.
Okay, so let's round off by seeing what we can learn from some turbo pump relics. These are historical parts from impacts and from experiments that are basically wreckage and debris. We've got a good collection here of parts. There's not enough for a complete turbo pump, so this is not a do-it-yourself turbo pump kit, but there's quite a few bits and pieces here that we can look at and learn a few things. Let's start with the bit that I've got in my hand here, which is actually a section of the fuel pump. We can identify its fuel pump very easily from these frog eye spacings. The frog eye holes here are the holes we see on the faceplate. We can see from how close these holes are together that this is definitely a part of the fuel pump. And if we compare it with the faceplate of a liquid oxygen pump, we can see here the spacing between the holes are much larger, except where we see something like this for the pusher. But otherwise, this is definitely a part of the fuel pump. A couple of things we can see here. One is the shape of the volute space. We've got a little paper piece here that goes in there. We can see that that would be the shape of the volute space at this point. And as it moves through, you can see how the volute space shape would actually change here. So this is giving us a snapshot really of the volute space. There's other things we can see on here that are quite interesting. One is this remains of the tracing of a M16 thread here, M16 course, and I've actually got one of the studs that would be used on the turbo pump here, and you can see it rather fits nicely into that, and then the bolt would do up onto the faceplate there. If I take the bolt that's the nut that's here off, this washer is still intact, and one of the things you can see about it is the washer is bent. It's actually a spring washer, and it's designed to stop the nuts coming undone. Sometimes you don't notice that when you look at these things, but this is a spring washer. Whoops. And if I just take this off gently, if I can possibly show it to you on the edge here, I don't know if you can see in that little gap there, and there's a little bit of it just there, we can actually see a bit of an O-ring seal. And if I take it apart carefully, so there it is, we can see the remains of a little section of O-ring that fits into that recess just there. It's a bit grubby, but you know, it was in the ground for about 80 years. So anyway, that's that section of the fuel pump. Another interesting item that we've got here is the steam jet. This is a complete cast iron steam jet from the turbo pump. It's a little bit broken off at one end, but it's pretty much intact otherwise. This is pretty much the size of it. We can see the angle here of the jets. If I use my pointer, we can see that the jet angles are something like that. As they go through, the steam enters on this side of the plate and moves through to be then applied to the turbine. We can see that this would be pretty much at this angle. This is an outlet flange, again I think from the swerve here, again from the A pump, the liquid oxygen side of the turbo pump. We've actually got the component that would have been mounted on here, and that's this choke. So this is something that would actually fit onto the outlet flange before going down into, for example, the liquid oxygen distributor. Now the Germans found there was just too much variation from pump to pump, despite their best efforts to keep the engineering to the narrowest possible tolerances of the time. Based on the findings of individual test run procedures, the pumps needed calibrating with chokes like this, so that the combined output from the turbo pump could be balanced to ensure that the correct mix of fuel to liquid oxygen arrived in the thrust chamber. The reason why the relatively crude agency of a choking ring was required, you appreciate these rings would be different sizes, is that they had no way of controlling the speed of the pump independently of the turbine. There was no gearing or anything they could adjust. You saw from the demonstration that the pumps actually run at exactly the same speed as the steam turbine rotor. So a method of choking was employed. You can actually see the chokes coloured red and blue in this picture from the Horst-Beck collection. You can see that the fuel choke is coloured red here, and the liquid oxygen choke is coloured blue, very clear on this picture. This is a blanking cap from the inlet throat of the turbo pump. Looking at it like this, I can't tell you if this is from the liquid oxygen or the fuel side of the pump, but I can tell you it was made prior to April 1944, because this actually changed in April 1944, or at least one of them did, and that's the blanking cap for the fuel side of the turbo pump. The blanking cap that we see here is nicely shown in this Horst-Beck image again, same image we were looking at a moment ago, and you can see the blanking caps looking very similar on both of the inlet throats, on the liquid oxygen and on the fuel pump. We can see on the cap that I'm looking at here, we've got the remains of two of the fastenings are still in place. Judging by the damage to the hole over here, this was wrenched off violently in an explosion. We can also see some traces of a gasket that was used to actually seal this up. This is the interior. The blanking plates on the Horst-Beck exhibit there, I think had only been put on temporarily, but they are actually the wrong way round. Now this blanking plate is quite different. Instead of, although it's the same size and fitting as the previous blanking plate we were looking at, this one has got a pipe union fitted to it, and this is part of the rotating line for the fuel pump. Now the thing to get here is that before late April 1944, when this design first starts appearing on the drawing boards at Peenemünde, the fuel blanking plate looked like this. After late April 1944, this component has been changed to this. And presumably they start turning up on actual missiles probably in early May 1944. The rotating line itself, not a new idea, but to actually pass the rotating line back to the fuel pump throat was a new idea that didn't really come in until late 1944. Previously, the rotating line was supplied about 10 or 12 inches higher up to a point immediately below the fuel tank, not connected to the turbo pump at all. You can see it quite nicely on this drawing. We can see what I'm calling the rotating line. That was a common name for this. It was actually a pipe that connected the fuel valve at the center of the thrust chamber, allowing a pipe to pass back. So after the fuel had been pumped into the inlet manifold of the thrust chamber, this valve actually allowed fuel back this pipe rather, allowed fuel back to the low pressure side of the turbo pump. Now previously it had done this by connecting to a point just below the fuel tank, and you can see it here in this drawing. We've marked it in red. You can see that this rotating line pipe or return pipe doesn't connect to the turbo pump. After late April 1944, we can see in this drawing the rotating line or return pipe connects directly to the low pressure side of the fuel pump, and it did it through the union that we see here. Now the reason why this was changed, why did they move it these 12 inches from the point just below the fuel tank onto the turbo pump, is quite straightforward. They found that the vibration profile of the turbo pump and motor were very similar, whereas the motor fuel tank vibration profile was quite different because they were connected to different parts of the missile. The turbo pump was connected to the thrust frame, which was also connected directly to the engine. So the resonance of the vibration was very similar for those two components. The fuel tank had a completely different vibration resonance because of the way it was connected to the rest of the body of the missile through a number of different soft connections. So it was far more likely to fracture or become damaged, and so they made this fairly simple modification of moving the return pipe away from the fuel tank and connecting it directly to the turbo pump. Look at a couple of slightly larger items here. Here we've got the faceplate for a fuel pump, seemingly uninjured and undistorted. We've got the face saver still attached to it here. This would have been providing a seal as the rim of the impeller would have sat in here, and this would have provided a sealing and self-lubricating point for the impeller. We can see the seals here. We can see a rubber or rubber substitute seal still intact here with a spring seal on the inside, seemingly intact. We could see another one on the inside here with a bit more damage. We can see the seating point for the overspin, the safety cutout switch just here as well, and some of the fastening still intact. And we can see the output point for the overboard dump for the lubricating and flow fuel used that found its way into this cavity. This was being used as a chicken feeder, I think, when I got hold of it, somewhere in Western Europe. Actually rather good as a chicken feeder, I think, one way or another. I'm no farmer, but I can see it from the point of view of the chicken, I think. Same thing again, this time the faceplate of the liquid oxygen pump. We can see a couple of interesting details on here. The flanging arrangements are quite different, a little bit simpler. This relied only on a very simple mastic seal, and it was actually quite difficult to get this face to seal properly with the liquid oxygen pump body face, and they tolerated a few drips with the pump without that being too much of a calamity. We can see here FTP, the manufacturer's mark on it, and we can also see, I think we've got a couple of marks here for Mabag as well on this face, as well as some numbers on the outside here. Thing to draw your attention to on the inside is we've got a set of bronze journal bearings set into this face. Instead of having an elaborate ball race here, we couldn't have any oil or grease coming into contact with the liquid oxygen, so a very simple journal bearing was used, and the liquid oxygen itself was used as the lubricant. Finally, we've got a complete or semi-complete oxygen pump here. The faceplate I was showing you a moment ago has been taken off here. We can see the fastenings. This was so badly distorted, it really was quite a job at actually getting that faceplate off here. A couple of things to look at. There's the bearing component that would have been in the bronze journal bearings I was showing you earlier. Here's the rim where the the surface saver bearing and sealer would have been running. We could see a set of holes on the inside. Some of them are threaded for some action that was made during the assembly process. We can also see on this face the remains of some sort of sealant, possibly a complete gasket. It was quite badly destroyed when we pulled the pump apart. I didn't think it looked like a complete gasket. I think it actually looked like some sort of sealant of some kind, you know, a hematite type product that was smeared onto this face before it was put together. Done very carefully, I'm sure, but nevertheless I don't think it was a gasket, at least not on this particular pump. I don't think it was a gasket. The other thing we can see here quite nicely is the eye of the liquid oxygen pump. Don't normally get a good chance to see that, and part of the splined, this very heavy splined shaft that's going into the liquid oxygen pump here. Now this end here would have had that flexible joint onto it. This wouldn't have been a continuous shaft as we're sealing. We've got one of the sealing rings here as well. Various parts are actually missing from here, but what we can see is the nature of the eye of the impeller there showing up quite well. Another little point to notice on this one, which is quite interesting, and it's a good way actually of dating it. Now this self-purge block is one of many features we can use on the turbo pump to give us some approximation of dating. Often not exact, because we can find these things on drawings, and then sometimes we have to make a bit of an estimate of when they might have actually been found on the pump proper. But this particular one, we know, doesn't really appear on manufactured pumps until after November, December 1944, and is a good way of looking at a cut-off point between the very end of 1944 and the beginning of 1945. And it's the case that most of the pumps you're ever going to see in museums, the great majority of them, because by their very nature they were pumps associated with the late war period, that's how come they survived, most of them will have this modified self-purge system rather than the very simple drilled hole, simply going from the inside of the throat straight through into the volute chamber. They've usually got this little block on them. Now the pump I showed you earlier on in this video actually didn't have this, so that's another good confirmation that it was a pump well previous to late 1944. So you can usually bracket things and put them in certain areas, and this is a good example of something that we can use to do that.
We can see some of the background history to this improvement of the self-purge system in this drawing of the turbo pump from August 1944. The original self-purge pathway, shown on the left in red, itself still a fairly new idea in 1944 and driven by pump failure experience, had to be drilled at a very steep angle through the narrow web in the aluminium casting, connecting the throat of the liquid oxygen pump to the top of the volute case. This was never going to be an easy shot. Any machinist will tell you drilling small, deep, precise holes in aluminium is no fun at the best of times. But you can see in this turbo pump from the late 1943-44 era, the low, shallow web made the job much harder, and especially harder to do quickly and with the minimum skill. At some point in mid-1944, the pump production specialists proposed the original web, shown here in red, be placed higher up in the throat to reduce the steepness of the drill angle and simplify this operation. The new higher web is shown here in green. Having to approach the metal at an angle like this, and with the cutter a long way from the head, just makes the whole job much harder and riskier too, with the ever-present risk of spoiling the workpiece, forcing a part to be pulled from the production line and either written off or passed for repair, either way reducing vital production volume. Even with the improved web position, it was still a slow two-stage process, requiring a small flat landing zone to be milled at the point where the drill cutter would be operating. The whole thing required highly skilled and slow setup to get every casting in precisely the right position for drilling. Even with these changes, the production team still needed a much easier way of machining the self-purge pathway. No such modification was required on the fuel pump. You can see in the inlet throat of the fuel pump on the right side of your screen that the self-purge pathway was much safer to manufacture, simply because the design of the throat allowed the drill to be presented to the metal at a steeper, more normal angle and for a much shorter bore length.
This was a stumbling block in the production of the turbo pump and needed to be simplified, and we see the effects of that simplification process here. We can see that they've added a lump onto the casting, so they took the old pattern and added this section on. So now the holes can be drilled very simply. They simply drill down once into the volute case and then one simple hole. Actually still not easy to do, a long small hole through aluminium. They make a single boring right the way through this part and into the flow casing. So don't forget this. So we're seeing the volute case here, the pump case, but just this area here, this open space with this vein splitting it, is the low pressure area of the pump. So if I put the pump up this way, the idea would be here, any gas, oxygen or anything else for that matter, air, that is in the top part of the pump here would vent back into the low pressure side of the pump. But if you look carefully at what's gone on here, you can see this actually hasn't worked very well for them. So they've driven a drill through, they've made a boring that goes right through the top of the pump and it comes out here. But if you look very closely, you can see here that the little piece of metal that should have come off has acted like a little trap door, and it's actually gone back into the hole again. Now they couldn't get access to this point very easily, so they haven't noticed that this has happened, and someone actually hasn't cleaned this hole up properly. You can see that if I put my probe in there, this hole is probably what? I don't know, a third of the size it actually should be, simply because the drill has gone all the way through. And then when they retracted the drill, it's actually pulled this little flap of metal back inside the hole again. So there we go. Was that anything to do with the failure of this missile? Well, we'll never know. This was actually a launch failure. This component was found in central Germany as part of, I think, a collection of components that had been studied forensically to see what the cause of the failure had actually been. Whether that was attributed with any failure, I couldn't say. So there is just some of the things that we can learn by looking at missile relics. Well, that's about it for this video. We've completed our overview of the gas turbine driven fuel and oxidizer pump system of the V2 missile. In part 2, we're going to be looking at the overspeed switch, and in particular the peculiar logic behind the overspeed switch in a bit more detail. We'll also be looking at how you can assess the health of the turbo pump by analysing launch footage, original launch footage of V2s in flight. in the next episode as well as looking at details like the gyroscopic phenomena associated with the V2's turbo pump. And the turbo pump as a source of some significant but unpredicted missile thrust. I know what you're thinking, but that's thrust over and above, well above, the trivial boost provided by the outlet of the steam exhaust system. So I'll leave you with that small mystery that we'll resolve next time. If you want to see more stuff like this, don't forget to subscribe, and do take a look at our website, v2rockethistory.com. And until next time, bye for now.